All right, so we're actually going to start on some different types of derivatives. I feel like everyone kind of knew this was coming. We talked about derivatives of polynomials. We talked about derivatives of exponentials. Now we're going to start talking about derivatives of trig, okay? So the first one that I want to start out with is sine, okay? All right, and let's try to see what the derivative of sine is by just maybe graphing it and seeing what happens, okay? Okay, so when we graph sine, we have to plot some points, right? Let me just draw out some points for you. This is the sine of theta. Theta is just another word for x that we use, very common with trig functions. We'll use a Greek symbol instead of like an x value. So I'll plot some values of theta and then we'll figure out what sine of theta is. Okay. So going back to our pre-calc classes, what's the sine of 0? Sine of 0. That one, it's actually 0, good. Okay, what's the sine of pi over 2? 1, good. What's the sine of, no, skipping ahead, of pi? 0. What about 3 pi over 2? -1. And then what about 2 pi? 0, good. Okay, these are kind of the the x-axis and y-axis values of our unit circle, but let's just plot those points. We got 0. I'm going to make the very top and bottom 1 and -1. Okay, pi over 2 we have 1, pi we have 0, 3 pi over 2 we have -1, and at 2 pi we have 0. Okay, so the graph of sine looks kind of like a wave. So the way that I like to draw this is to connect the dots, making my little sine wave shape. This is actually pretty good. Okay, and sine isn't just between these two values. It continues on and it kind of repeats itself every 2 pi, okay? All right, so even though we don't know the derivative of sine, we can still figure out what it might look like using the graph. And the way we'll do that is we'll think about what we learned about a little whiles back when we talked about what the derivative actually means, okay? Let me just talk about these turning points, okay? So at the turning point, we know that the tangent line is horizontal. What does that mean about the derivative at pi over 2?
That's 0.
0.
Good. So at pi over 2, the derivative is 0. The same thing happens at 3 pi over 2 because it's a turning point, right? So the derivative is 0 here. Okay. So if I go to my graph of the derivative of sine theta, I know that the derivative at pi over 2 is 0. And I know that the graph of the derivative at 3 pi over 2 is also going to be 0. Okay. Now we also talked about positive, negative, and constant derivatives. And we said that translated into a graph being increasing, decreasing, or constant, right? So between 0 and pi over 2, the graph is increasing, right? So what does that mean about the derivative?
That's
Positive, right? So from 0 to pi over, so this is increasing, which means from here to here, this derivative is going to be positive. Okay. Okay, from pi over 2 to 3 pi over 2, the graph is decreasing. What does that mean about the derivative? I mean negative. So from here to here, our derivative is negative. Okay, and then finally from 3 pi over 2 to 2 pi, we also have an increasing function, which translates into a positive derivative. All right. So, okay, so this kind of gives us a little idea of what this graph looks like. I'm going to give you 2 more pieces of information that might be hard to look from the graph, but I'm just going to kind of hand to you, okay? At the point 0, I'm going to say that the slope of the tangent line, m tan, is 1, okay? That slope is just 1 there, okay? It's also the same here. So the slope of my tangent line is 1, which means the derivative is 1 there. So I'm kind of just giving you a free point here. Okay. And I'm also going to tell you that the slope of the tangent line here is -1. So it's decreasing at -1. Okay. So I'm kind of giving you a free point here. Okay. Looking at the pieces that we have of this graph right now, is there anyone who can tell me a guess of what the derivative of sine is?
It's a cosine wave.
It's a cosine wave, right? If I connected these points and kind of looked at, okay, where we're positive, where we're negative, and where we're positive again. Let me see if I can draw this in maybe green. The derivative is going to look like this. That's actually pretty good for my drawing ability there. Okay, and this is the graph of cosine. Okay, so the derivative of sine is cosine theta. Okay, at least that's our guess. Okay, is there a way to definitively prove what the derivative of sine is? What do we always have to fall back on with derivatives?
The limit definition.
The limit definition, right? So I know that we've kind of strayed away from the limit definition, but we can always fall back on it, and that's what we're going to do. Okay, so let me take our function. I'm going to give it a name, f of x. And I like using x instead of theta, so let me just change my function into f of x equals sine of x. Okay.
Does the cosine theta have parentheses?
No, it actually doesn't matter. So I can write it like this. But since theta is just by itself, you don't actually need to write the parentheses. Okay.
Well, by itself, that's still there.
Because this is function notation. Okay, so function notation always has the parentheses. If I'm just writing the function how it's defined, you don't need the parentheses. Okay, so we're going to use the limit definition to find the derivative of sine. This takes a lot of space, so I do have a blank back of the sheet of paper too, if you're still copying this down, and it takes a lot of space. Okay, and the word I'm going to use to say that I'm finding the derivative of this using the limit definition is I'm going to say I'm going to derive the derivative. And derive just means to find using like information that we had from before. Okay, so who remembers the limit definition of the derivative? It's been a while. Good. So f of something minus f of something.
Oh, you're doing the actual, okay.
Yeah.
Over delta x.
Over delta x. What goes in the first blank?
Sine of x. Delta x.
Not sine, but
X.
x plus delta x. And then this one's just x, right? Okay, this is the limit definition of the derivative function by itself. Okay. Well, instead of writing f, I can write sine, right? Because f just means take the sine using our definition of our function. So instead of this, I'm going to write the sine of x plus delta x minus the sine of x over delta x. Okay. Now, this is kind of a tricky question, but does anyone know how we can make this a little bit easier to work with?
Sine conjugation, isn't it?
Not quite.
Can
Sam,
you split the fraction into sine x plus delta x over delta x minus sine of x?
that is a thing. We can do that. I'm not going to do that yet because I think it makes it a little bit more confusing. But that is a good step that you can do. Cool. Does anyone know a formula to split it? All right, I'm gonna spoil it for you guys. There is a trig identity called the sine addition formula. And I don't think I showed it to you in class in pre-calc, but oh my gosh, did I spell that right? Yeah, sine addition formula. And I don't really want to prove this right now, but I'm just going to give this to you. We're going to kind of cheat a little bit. it just says that the sine of a plus b is the sine of a times the cosine of b plus the cosine of a times the sine of b. I know it's been a while, but there is a formula that kind of just tells us that. Okay. Okay, so rewriting this limit as delta x goes to 0, what does the sine of x plus delta x turn into? Sam?
Would it be sine of x times cosine delta x plus cosine of x times sine of delta x?
Perfect. Okay, and I also have to keep the minus sine x over delta x. Okay. Now, talking about parentheses, normally when there's just one thing after the sign, you don't need parentheses. Of course, you can put it if you don't want to. Since the delta x has like 2 symbols in there, I'm going to put parentheses around it just because I don't want to confuse it as like multiplication or something. Okay. I'm going to do something a little weird right now, just to make things a little simpler. And I know this might be confusing right now, but I'm going to take, let's see, I'm going to take this guy here and this guy here, and I'm going to just swap them, okay? And the reason I'm doing that is because I'm seeing that, let me see, the first term here and the second term here both have a sine x. I kind of want to group them together, okay? Oh, do you mind passing this back? Okay, so the only thing I'm going to do is swap the 2 things I've highlighted, okay? So sine of x, cosine delta x, minus sine of x, plus cosine x, sine of delta x, over delta x. So I just swapped it. Okay. Now, Sam, what was your suggestion to me in the beginning?
You can split up the fraction, and I think you can factor out sine of x. So it looks like
Yeah, right. So maybe we should split up the fraction using this addition symbol here. Okay, so I'm going to split this into 2 different fractions, keep the first 2 terms clumped together and the second 2 clumped together, and maybe we'll be able to factor something out from there. Okay, so this becomes the limit as delta x goes to 0 of, I'm going to put this whole limit in parentheses so I don't get confused, sine x cosine delta x minus sine x over delta x. Okay, and I'm going to add on the cosine x sine delta x all over delta x. Okay, so I kind of just split this into 2 different pieces of addition. Okay, I think Sam told us that we can factor out a sine now. So let's see if we can do that. We have the limit as delta x goes to 0. What happens on top when I factor out a sine x? What goes in the parentheses?
cosine of delta x minus 1.
Good, cosine of delta x minus 1. Okay, all over delta x plus cosine x sine delta x all over delta x. Okay. All right, at this point, I've run out of space, so I'm going to do something weird. I'm going to take this, and I know I'm kind of cheating here. I'm just going to copy it and move it to the next page. Okay, so we're moving on to the next page here. Right here. Okay, from this step, any ideas on what we can do? Does anything look familiar to us? Trig identity. We can do trig identities. I'm going to tell you it's going to make it a little bit harder. Anything that we've done in class involving limits and sines and cosines.
Cosine minus with the sine.
The sine. What do you notice about the sine? What does it look like?
It kind of looks like our not derivative of it, but the
Oh, it's sine of delta x over delta x equals 1.
Yeah, so you're saying it looks like this. The limit as x goes to 0 of sine x over x goes to 1, right? And there's another one that we looked at, right? The limit as x goes to 0 of 1 minus cosine x over x. What did that one go to? 0, right? So these two are going to kind of pop up at us as we go forward. But maybe we can make this limit look like a combination of those two. Okay. Now, these guys are swapped, right? Is there a way to make the signs look different but have the same numbers? Did this on your homework. Is there a way, if you look at this guy here,
Multiply by
the cosine delta x minus 1 and the 1 minus cosine x, they're the same values, but they're swapped. So one of them comes first, the other one comes later. So they just have different signs. Is there a way to kind of make this look like this? Not with subtraction.
No, subtraction.
Commutative only works for addition, right? Yeah, factor out a -1. You did this on your homework when I gave you a question that was a little bit too hard for you guys that I didn't talk about in class. But if I want to make it look like 1 minus cosine x, I can just factor out a negative. And it would turn into negative cosine x plus 1 or 1 minus cosine delta x. Okay. So if you factor out a negative, you can kind of swap the signs or the position of the subtraction. Okay. Okay, so now this is looking a little bit more like the two identities that we have, okay? Instead of just kind of doing it in our heads, I want to split up the limit in a specific way so we definitely see how the limits come about. But at this point, you can probably see where this is going to. Okay, whenever I have an addition inside my limit, I can always split that up into two different limits, right? So this would be the limit as x goes to 0 of sine x, 1 minus cosine delta x over delta x, plus the limit as delta x goes to 0 of cosine x sine delta x over delta x. So I just split up the limit of addition into an addition of limits, okay? And when we have multiplication of limits, we can actually split that up into two different multiplied limits as well, okay? So what I'm going to do is I'm going to take the sine x and the cosine x and split them into their own limits. So this is the limit as delta x goes to 0 of negative sine x, the limit as delta x goes to 0 of 1 minus cosine delta x over delta x. I'm going to split up the second one in a very similar way. The limit as delta x goes to 0 of cosine x times the limit as delta x goes to 0 of sine delta x over delta x. Okay, so all I did was split up everything into their own limits, and now we have those identities right up on top, right? Okay, let's go through each of these limits. What's the limit as delta x goes to 0 of sine of x? What am I plugging 0 into? Delta x. Is there any delta x in my phrase here in sine of x? So do you see a delta x here? No. So what's the limit? As negative sine x. Good. Okay, so if there's no delta x, you're not plugging anything in. It's literally just a constant function. We're left with sine x here. Okay, what's the limit as x goes to 0 of my 1 minus cosine delta x over delta x? 0, good. Okay, now we're going to add on, what's the limit as delta x goes to 0 of cosine x? Cosine x, good. And what's the limit of sine delta x over delta x? 1, good. Okay, 0 times negative sine x is 0. Plus 1 times cosine x is cosine x. We're left with cosine x. So it looks like our prediction was right, and the derivative of sine is cosine. I swear that was a lot of work. I promise you I'm not going to make you recreate that. I think that was a lot of work, but we got there eventually. Okay, so two trig derivatives that I want you to memorize. If you don't memorize them, you have to do the limit definition, and I know you don't want to do that. So let's actually memorize these. The derivative of sine is going to be cosine, and the derivative of cosine is negative sine. You can find this using the same way, so you can use limit definition to find this, okay? Kind of weird that the derivative of cosine is actually negative, but that's just how it is. Okay. Any question on these two derivatives? I want you to memorize these. And let's continue on. Okay. Well, you know what the derivative of sine is? You know what the derivative of cosine is? Let's talk about tangent, okay? So we're actually not going to use the limit definition to find the derivative of tangent. It's actually kind of hard to do it that way.
Secant squared.
I think I heard someone say it.
It's secant squared.
It is secant squared. How do you know that?
I just because I took calc before.
Okay. Do you know how to derive it?
No
without
idea.
using the limit? No idea. Anyone else? The quotient rule. And why is it the quotient rule? There's no quotient here.
It's sine as a cosine.
Yeah, tangent is sine x over cosine x, right? So that's where our trig identities come in. Okay, so instead of saying tan, maybe I should just say sine over cosine. And now we can use the quotient rule, knowing what we know about sine and cosine. Okay, so quotient rule, f over g prime. Can someone tell me what the quotient rule says that this is equal to?
Cosine of x times,
Oh, okay. Can you do like with g and f? Sorry.
g of x times f prime of x
Mhm.
minus f of x g prime of x
Mhm.
over g of x squared.
Good. All right. And using this notation, I know that f of x is the whole thing. For now, for the setup, let's make the top f, the bottom g, and just kind of forget that the original function is called f, okay? Okay, piecing this together. I know that g is cosine of x. So that is g, okay? What's the derivative of sine x? Cosine, good. So that was f prime, okay? We're going to subtract off f, which is sine. Okay, so that's f. And what's the derivative of cosine? Negative sine, good. And we're putting that all over g squared. So this is g prime. We're putting this all over g squared, cosine x squared. Okay, I think we can clean this up. Cosine x times cosine x is cosine squared x. The 2 on top just means that we're squaring, okay? We're going to subtract off, subtracting a negative makes a positive. So this is sine squared of x over cosine squared of x. Okay. I think I heard Liam say that the derivative of tangent is secant squared. That doesn't look like secant squared. Anyone know how to make it look like it?
Oh.
Yeah.
Cosine squared of x plus sine squared of x equals 1.
Perfect, right? Remember this trig identity, okay? Uh-huh.
Cosine x, all that being squared, go into oh, there it is. Okay.
Oh, sorry. Yeah, I kind of just moved the 2 up top to make it easier to look at. Hmm?
Or
No, so we don't distribute this 2. This literally means this. So it's kind of like shorthand notation to say cosine squared, because I don't like writing parentheses around stuff. So this literally translates to this. Yeah. Okay, so let me just remind you of a trig identity that you might have learned a while ago. The one that says sine squared of x plus cosine squared of x equals 1, right? Okay, so literally everything up top turns into 1. And the bottom is still cosine squared x. Okay. I don't really like working with squareds when I deal with trig identities, so let me just write this twice. This is the same as cosine 1 over cosine x times 1 over cosine x. Okay. Think back to your trig identities. What is 1 over cosine of x? Secant, good. And then the other one turns into secant as well. So that's why the derivative of tangent is secant squared of x. Okay. Now, I'm not going to do the other identities because I think deriving them, deriving the other trig formulas is very similar to the deriving the tangent. So we won't do that. But what I have here is a list of all the derivatives of our trig functions, okay? So the derivative of sine is cosine. The derivative of cosine is negative sine. Tangent becomes secant squared. And we also have the other ones that we don't use that often, but cosecant, secant, and cotangent, okay? These are also derivatives I need you to know, to memorize, okay? Cosecant becomes a negative cosecant, cotangent, okay? Secant becomes secant tangent, and cotangent becomes cosecant squared, but a negative, okay? Now, I know this sounds like a lot to memorize. The first two are kind of things you have to know. They're just kind of opposites of each other. If you take a look at this, it looks like the tangent and the cotangent look really similar, right? And they both have tangent in the name, okay? So all you kind of have to know is they look very similar and know which one goes with which. The cosecant and secant look very similar and they have each other in the name, okay? So that's another way you can think of when you memorize these. Okay. Any questions before we go on? All right. Flipping over to the next page, let's see how we can use these derivatives to solve some problems. We'll kind of piece everything together later, and then we'll piece even more rules together at the end. Okay. So for example, let's say I want to differentiate or take the derivative of secant x over 1 plus tangent x. Okay. What rule are we going to use here? Quotient rule, right? We have a quotient, so definitely should use the quotient rule. Okay, the quotient rule says f over g prime is what? Gosh, good. Minus. Perfect. Gf prime minus fg prime over g squared. Okay, the top is always f, the bottom is always g. Okay, g is 1 plus tangent x. And I'm going to write it down here just because I want to write on top of it. Okay, I'm going to multiply that by f prime. What is the derivative of the top? Good, secant x, tangent x. So just using the identities or the derivatives that I gave you, that's what the derivative of the top is. I'm going to subtract off f secant x times the derivative of g. What's the derivative of 1? 0. What's the derivative of tangent x? Secant squared. Good. Okay. And this is all over g squared. So 1 plus tangent x squared. All right. Honestly, I probably would want to clean this up on a test or quiz. So let's just write this a little bit easier. One thing we can do is, I guess I can multiply the secant tangent over to the 1 and the tangent, or I can distribute that, okay? So secant tangent times 1 becomes secant tangent. What's tangent times secant tangent?
Secant tangent squared x.
Yes, secant x, tangent squared x. Okay, and then secant x times secant x times secant squared would be secant cubed x, all over 1 plus tangent x. Okay, that's fine for a test or quiz. I guess we can do a little bit more. Anything we can do up top? what does everything on the top have in common? Yeah, we can take out a secant, right? That's perfect. So this would become secant times, secant x times tangent x plus tangent squared x minus secant squared x over 1 plus tangent x squared. Okay. Anyone see something we can do?
Factor out.
Can't factor out a tangent x.
Oh, wait.
Any identities we can apply here? I wouldn't quiz you on this on a quizzer test, but this is just for fun. What's tangent squared x minus secant squared x? Not quite. It's -1, good. If you notice that, that's fine. I would honestly take this answer, but just for fun, let's do this. Secant x times tangent x minus 1 over 1 plus tangent x squared. Okay, so this is for fun. Okay. Any questions on what I've done here? All right. I think I'm gonna give you a crack at example 2. We might not get to explaining this one before the quiz review, but I want to give you a few minutes to work on this one on your own or in groups. All right, let's go through this one. John did a great job of writing example 2 down. All right, so example 2, we wanted to find the second derivative of secant. John, do you kind of want to take us through your steps here?
So you find the first derivative first, and derivative of secant is secant theta times tangent theta, and then you do product rule. So that comes out to the secant tangent prime is secant squared times secant times secant squared, or no, secant squared times secant plus tangent times secant times tangent, and then you just simplify it in the next step.
Great job. You could have taken out a secant, that would be fine too. As I've been walking around, I saw that. But I think this would be great for a test or quiz. All right, before we go on, I think we have a quiz review to do. So let's hold off on this until next class. Just like last week. If you have somewhere to be, I am not offended if you go. But I will post the answers to this by probably this afternoon.